This is the Physics Unit 3. We are on page 6, about halfway down. We are going to be looking at example 3, 4, and 5 in this video. For example 3, a frictional drag of 30 newtons exists between a cart and the table. So this is a new type of force that we're talking about here. Frictional drag, or something we could call the force of friction. Capital F with a small subscript, lowercase s, excuse me. F sub F, or we could just call it the force of friction. 30 newtons exists between a cart and the table. This means that if we exert a pull of 10 newtons on the cart, the frictional drag is greater. It will not move. If we exert a pull of 20 newtons on the cart, the force of friction is greater. It will not move. If we exert a pull of 30 newtons on the cart, it's actually not going to move. If we exert a pull of 40 newtons on the cart, it will accelerate. So we're going to draw some diagrams. So first off, I'm going to write force of friction equals 30.0 newtons. So there's going to be 4 pictures drawn here. Actually 5. So in the first one, we're going to be basically drawing, here is the table, here is the cart, and we are drawing a force diagram. So for this first picture, we are exerting a pull of 10 newtons on the cart. So here's our pull. It is 10 newtons. And force of friction is 30.0 newtons. Now take a look at this. This said that if we exert a pull of 10 newtons on the cart, it will not move. But looking at this picture, there is an unbalanced force, a net force, which would tell me that this would probably move. And the problem with this one, this is actually a bad picture. So let's label that as a bad picture, and we'll box it off right here. The reason it's bad is because it looks like we have a net force. Fix this right here. Here's a better version of the same picture. So we have the table. Here's the cart. I am exerting a pull of 10 newtons. This says it won't move, and it won't move because there's a balanced force. The force of friction is 30 newtons. This is the maximum amount of force that friction can provide here. So the friction is up to 30 newtons. So when I pull with 10 newtons, friction is preventing it from moving with 10 newtons. It can have up to 30, but it's only using 10. If we exerted a pull of 20 newtons on the cart, it wasn't going to move. So same table, same cart. Now I am pulling with 20 newtons. And it's not moving, which means there's no net force, which means this 20 newtons has to be balanced by the friction, which in this case is 20 newtons. If we exert a pull of 30 newtons on the cart, draw this up a little bit. So I'm exerting a pull of 30 newtons. It will not move because the friction can exert a force of up to 30 newtons, and this is balanced. There is no net force. Both of these forces balance each other out. In the final scenario, if we exert a pull of 40 newtons on the cart. So here is the table. Here is the same cart. My pull is 40 newtons. In every other scenario, the friction was equal to my pull. My pull of 10, the friction was 10. My pull of 20, the friction was 20. My pull of 30, the friction was 30. The frictional drag is 30 newtons, which means maximum. The maximum amount of frictional force is 30. So in this situation, the most friction that can occur is 30 newtons. And now we have an unbalanced force. And we're going to have acceleration. Acceleration goes in the direction of the net force, which in this particular picture is to the right. The forces going right are greater than the forces going left, and so my acceleration is right. The frictional drag is the maximum amount of resistance that friction can use to oppose a force. So calculate the acceleration of the cart, mass of 40 kilograms, if the force is exerted on 40 newtons. So we're still on example 3 here. So let's take a look. Acceleration is force divided by the mass. And so if we're just quickly looking up here, we see 40 newtons as a force. That's how much we're exerting on it. We see the mass is 4 kilograms. And so we say 40 divided by 4 is 10. Newtons over kilograms is meters per second squared. And then we think, hey, we're done. But actually, this is wrong. Why is it wrong? The total force exerted is 40 newtons, but we have to include friction. So let's go back and try this again, but let's be a little more careful to pay attention this time. So acceleration equals the net force divided by the mass. And the net force, so really we're looking at this picture right here. So we have 40 newtons, 40.0 newtons, minus, and the force of friction is in the opposite direction. So 40 newtons minus 30 newtons divided by the mass, which is 4.0 kilograms. And so we have a net force of 10 newtons and a mass of 4 kilograms. And so the actual acceleration here is 2.5 meters per second squared, because we had to account for the friction. So it's this one. Include the friction. Number 4, find the mass of an object which accelerates at a rate of 3.2 meters per second when a net force of 160 newtons is applied. find the mass of an object. So the mass is the force divided by the acceleration. Just a quick rearranging of this formula up here. So in this one, the net force, it tells us the net force is 160 newtons. So in this example, they have already included everything. There's already the force of the pull, there's already the force of friction included. All of that plays into the net force. So net force is 160, and the acceleration is 3.2 meters per second squared. And so the mass of this object must be 50 kilograms. So take a look at the difference in the terms here. Up here in example 3, it said if the total force exerted, that means how hard we pulled on it or how hard we pushed it. Here it said when a net force of is applied. So total force and net force are not necessarily the same thing. A 6 kilogram cart is dragged across the floor with a force of friction of 4.0 newtons. What total force must be applied to accelerate the cart at 8 meters per second squared? So we know the mass of the cart. We know the actual acceleration. If we multiply colors, this, if we multiply these two things, we will get net force. So net force equals mass times acceleration. So the net force equals the force of the pull minus 4 newtons for the friction. So we're going to put this in over here. The net force so here we're looking for total force, not the same thing as net force. So we know the net force is the force of the pull minus the force of friction. So here is the force, we'll say just F, minus 4.0 newtons equals 6.0 kilograms times 8 meters per second squared. So net force equals 6 times 8, and that's what we were looking for here. But we want to know the force of the pull. So the net force is F minus 4. The net force is also 6 times 8. So let's go ahead and see what we have. Force minus 4 newtons, and this is 48 newtons as the net force. And so add 4 newtons to get rid of this, so plus 4 newtons to this side, and the force of the pull is 52 newtons. So the force of the pull is 52. If you subtracted out the 4 newtons for friction, that was the net force of 6 times 8, or 48.